show you where the lab information is and talk a little bit about having lab today. Let's see. So there's two ways to get to the lab information. One is to go in here, right? Anywhere there's a little triangle, you can open and close it. And we did the lab safety already. There's a safety video, so that's about 30 minutes long, and you should definitely watch it so that you move forward with that knowledge. And then today we're going to work on Introduction to the Metric System. And we'll see what we can do. Oh, I forgot to take this out. We're not checking in because we're not in person. But down here, this is what I call the lab block for experiment 1. And you can get there another way. If you leave that closed or open, doesn't matter. You can go to the day that you're looking at. So if you wanted to look at lab 2, you could click on Monday the 27th, but today we're on the 20th. So then I'll come down here and click on Introduction to the Metric System. That's going to put me down below into the proper place. So you can just click there. And we're actually doing experiments, so we would be considering lab safety, making sure that we have closed shoes and full coverage. And then here's the lab manual pages. I think I opened this up a couple days last week. And there's quite a lot of reading for the first one. So the policies and safety, some guidelines. Now the visual guide to lab equipment, we're going to talk a little bit more about that. That'll be useful. So if you're reading the introduction, you'll look back at that guide to figure out what they're talking about. Bunsen burners. And then here we get to our introduction material. And we haven't addressed all of this stuff, so we're really launching into some new content today. Let's see. And then here's the pre-lab assignment. So you have preparing your notebook, and you have answering these questions. Now these questions, I use this to program our pre-lab into WAMAP. And then after that, we have our data tables. So hopefully you have copied these into your notebook so that when you see the data, you're able to just enter it in. All right. Okay. So these are the data tables. I'm not sure if we're going to do part C. We'll see. And then we have the post-lab questions. So these are available to you. If you can print these double-sided. And it's a good idea to just print this all out, and then you have the paper to work on. Okay, so that's where the lab pages are. I want to make sure we're all on board. Some people have done the pre-lab. You can see it's in red here. The pre-lab is due. And I made that too. Let me just click down here. You can see how it's pink. And so that's today. That's the one I've clicked on. I could also look at what's on the quiz for Friday, chapters 1 and 2. But today, the pre-lab is due at 11 a.m. So I gave that some extra time because I want to make sure we all know how to do those problems. And in order to do the post-lab, which you'll see is due in 1 week, I made that due at 9 a.m. before class. We could consider it due at midnight on Sunday, but yeah, I don't want you to be spending class time doing lab work. So I just made it due at the beginning of class on Monday. Let's see. So in order to open and complete the post-lab exercise, which we'll do today in lab time, you have to complete the pre-lab and get a passing score. So some of these setups, this programming, the questions, I know in the post-lab there's one question with lots of parts, and they're probably all going to be marked wrong because I just had some trouble with the programming and the automatic grading. So don't worry if it's marked wrong. I will go in and correct those answers. So when you see it's red but you have full credit or you have a score there, know that the score goes in your grade book. And so I'll go back in and be grading those manually. even though it looks like it's marked you wrong. Okay. So that's kind of how the post-lab, the pre-lab and post-lab is going to work. So you don't need to be working on the pre-lab right now. What we need to do is understand the content first. Talking about units and observations. So we have qualitative observations, things like that describe the qualities. You know, those could be the physical or chemical properties, or we could say, you know, we have roughly half men and women in the classroom. That would be, I guess that's a little bit quantitative. We could say most of the students in the class have dark hair. That would be another observation. Or we could say one student has purple hair, something like that. That would be describing the qualities. But we're really going to be concerned with tightening up our ability to, I did record, right? Is it recording? Yes, okay. We want to tighten up our ability to express quantitative measurements accurately. We want to be able to write numbers that reflect our measurements accurately. And so that always requires a unit. Even in elementary school, they began teaching that you have to have a unit, because if I came in and I said, hi, 18 today, you don't know what that means, right? So we always have to have a number, a unit associated with a number, so that we can compare those numbers and so we know what we're talking about. So we'll keep our units on every number we write. And that's really important. We probably have some experience with that. Just taking your temperature, right? Or cooking, measuring out amounts of stuff that we would put together. And anytime you make a measurement, there's some level of uncertainty associated with it, and it depends on the measurement device. So it depends on what measurement device, what marked scale you're using to measure it. So that's really what we're concerned with in our lab today. So we're going to use graduated cylinders. Here's an example of one, and this shows blue for the water level. So we know a couple of things about where that is just from this picture here. Here's our 15. That longer line is the 15, 16, 17, 18. So we know right away that that measurement is between 17 and 18, which means we know this value here. All right, I wanted to get my little spotlight so you can see. We know that it is 17 point something because it's more than the 17 mark, but it's not yet at 18 mark. And so when we read this, we are required to make our best guess in between the markings. So that's the content of today's lab. You always need to go to 1/10 of the smallest marking in there. So we would guess at that number, and we would look closely. We have to look flat onto the line so that we see it, not looking up or down at it, but looking straight on. And so here we might guess a number here. Maybe if you want to enter in the chat some of your ideas of what that measurement might look like. So we know it's 17, but what would the number here? 16, 17. Anybody have an option? 17.8. Yeah, this line right here looks like it might be a 0.8. And in the next slide, I'm going to tell you, we always measure at the bottom of the meniscus. And so that would be like, we want to look at this point right here. So 17.8 would be an acceptable measurement. Get it right on the bottom of that meniscus and then draw it over. So the bottom of the meniscus, I might call that 17.5, and that's okay. They don't have to match. So if Zed makes one measurement, then he would want to make the next measurement too to make sure that he's consistent. But that's pretty well within our measurement, right? So the important part is that you have the that digit filled in. Whether it's an 8 or a 5, I would tend to say 5 or 6, but that's what we're going for. It's the number of digits. Okay, so make sure you get the number of digits. Does that make sense? That's what we'll be doing in lab today. So I have some glassware here. I'm going to try and hold it up really close. Maybe put something behind it so that you can measure it. Okay, so that's what we'll do in lab. And some of them are photos that I took earlier, so you'll see it on screen. Okay. There we go. Okay, we're going to write down the numbers, and I'm going to go a little bit quickly through the slides so we actually get to doing the problems. But that number of digits, in that last one we had 3 digits, 1, 7, 5. All right, this is just some rules for you to refer to and some measurements. I'm going to skip through these. Here we go. Here's another graduated cylinder, and we have to read at the bottom of the meniscus. I have a better picture from this, but I want to show this is a large cylinder. This is a liter. So it's up here is 900, here's 1,000 milliliters. So the longer mark here is the 950. So we can count those 910, 920. Oh, let me get my little spotlight. Maybe that's better. 910, 920, 930, 940. So it's more than 940 and less than 950. So we have to make a guess to 1/10 of that smallest digit. So we'll say 946. So the units on that marking scale tell us how many places to put in our measurement. All right, now this one really shows that meniscus. This is a different kind of measurement. This is a burette. So it starts with 0 at the top. When it's completely full, it's 0 at the top, and then we open the little valve down here, and we allow the water to drain out, or the liquid to drain out the bottom, and then we take another measurement. And so we'll always be looking at how much was delivered from beginning to end. So when we read this, we have to read in the downward direction, which means that here's 20, here's 21, here's 22. And do you see how the bottom of the meniscus is just below the line? It's just below that. Let me see if I can get this. All right, and then I will move it up. And they wrote their line, but I kind of left it showing. So here was 22. Here's 23. We need to go to 1/10 of a milliliter because the markings are 1 milliliter. So we can just pick 22.2. We always read at the bottom of the meniscus. So, Jed, I think what you were seeing was that the top of that meniscus was a little closer to 18. And the bottom of the meniscus was kind of in the middle, was more in the middle. Does that answer your question? 17.8 would be a fine measurement. On that meniscus, it wasn't super clear, but we always want to read from the bottom of the meniscus. All right, we'll always show all of our digits. Usually we use a little weigh boat on the balance just to keep it clean. On some of our examples, I just put the object on the balance pan because it's not something that will contaminate it. But if you're ever measuring a chemical, a powder, or a liquid, you would always use a paper there, a weigh paper. All right, let's do this one. I'd like you to write down the digits or show me in the chat the digits of the measurement that you would make here. Right, so we're going to look at the end of this object. So we know it's between 4 and 5. We get 4 point, and then we have to go to 1/10, so 0.1, 4.5 centimeters. Perfect, thank you. All right, what about this one? This looks like the same object. How would we express that value? We need one more digit. So we have 4.5. We know it's bigger than 4.5, but less than 4.6. So let's just say 4.55, 4.56 centimeters. Always write that unit. Yeah, 4.57 would be perfectly acceptable, right? That's right within that. That's your educated guess, right? That's your job as a scientist, is to make that guess. So it doesn't have to match exactly what someone else says, but it has to be just variance in this last digit, right? So we could see a different number in that last digit. All right, C. What would our value be for C? Looks like you've got that right. So here, would 3 centimeters do it? We have to go to 1/10 of the smallest marking. So we would have to show that 0. That looks like it's right on the line. So we have to show that 0. Okay. We don't need the other one. Now, if we were using the ruler, if we were using this ruler for this object, then we would write 3.00. It's the ruler that tells us how many digits to write. So to find that out, I'm going to think about what's the distance between these two markings. That is 0.1 centimeters is the distance there. So we need to go to plus or minus 0.01 centimeters. Let me align that. We always have to line up our decimal place. Oh, 0.2. That should be a 1. Oh, darn it. Well, I can't fix my text, but it should be plus or minus 0.01. So that's what tells us how many digits to write in the answer. All right, we'll get lots of practice with this. Okay, I think, let me just take a look here, go back to my mouse. Yeah, we have some exact numbers, right? So not everything is measured with a device. For example, there are 22 people in this meeting. That's not measured with an uncertainty, right? That's exact. That's an exact number. All right, I'm going to let the rest of this go. All right, inside course resources, we're going to work on worksheet number 2. So these do not always correspond to the week. It's not always Monday that we start a new one, but we'll start number 2 today, week 2. All right. So again, things are moving a little slower, so I'm going to skip through some of the activities. You are welcome to work through these. Measurements as a number with units attached. And then here's some data. It's a little bit old, 2013, but the trends are clear. So this is looking, I like to talk a little bit about reading graphs, but again, it's not one of our core outcomes. And so that's one of the things we'll talk a little bit about it and then keep moving. Notice that, oh, let me get my annotation bar and bring it over. So notice that there's 0 here. This is the temperature anomaly. This is the difference in temperature from an average. And that average was measured in a historical pre-1965 value. And so you can kind of see it was lower through here. And then since the 70s, it's been trending upward. So in our first exercise, this is asking us to read the graph and take a look at those differences. Okay, so if you have questions, you are always welcome to post in the forum. I might be able to scan in some solutions, but I don't have access to campus, so I don't have a double-sided scanner. But I could definitely answer questions on any of the worksheets. If you have them, please feel free to post on the forum. All right, so here's what we're really focusing on today is using the tools to show a number that gives you an accurate representation of how that was measured. We have some different units, length. We talk about feet and yards in the imperial system. Mostly in this class, we will be working with metric system, but we will use a little bit of imperial units to learn how to convert between them. All right, this is really important. This is kind of what we're looking at here. We have 3 different rulers, and we're going to look at what is the increment, so the distance between that smallest marking, what is the value of where that line is, and then here it is blown up on a bigger scale. What the uncertainty is, so that's the plus or minus 1/10 of the smallest increment. And then how many significant figures, how many digits are significant in that measurement. Okay. So it's always 1/10 of the smallest markings. You're always going to guess in between. All right, so I'll keep this up on screen, ruler A. And feel free to write answers in the chat box. Right, so the increments on the smallest, these are a centimeter ruler. We're just going to assume these are all centimeters. Right, so always write your number with a unit. The increments on here are 1 centimeter. Right, the distance between the lines. So what would we call that measurement? Your numbers may be different. Feel free to type some into the chat if you care to. Just looking at that top ruler, I might say that looks like about 4.2 centimeters. All right. Maybe I can make this bigger. There we go. So now I've included that uncertainty. And then we're going to look at the number of digits here. Right, so just how many digits are significant is 2. And I often call them SF, significant figures, or sig figs. All right, on ruler B, now we have more lines on our ruler. So those increments are 0.1 centimeters, right? The distance between the smallest markings. That means our value now has to be a little bit more precise, 4.2 0.5 centimeters, for example. And then writing that with the uncertainty, 4.25 plus or minus 0.001 centimeters. And thank you, Zed, for showing your answers. 4.3 would be perfectly acceptable for A. 4.35, that one's not quite right because check out where that is. And this is really helpful. 4.1, 4.2, 4.3. It's below the 4.3 line. So you could change in the 5 position, but anything that didn't start with 4.2 would be incorrect. And 4.24 would be perfectly fine. So that's just a matter of judgment, a difference in opinion, and that's fine, right? That's the variation in our judgment, and that's totally acceptable. It's within the accuracy of the device. All right, and so that number from ruler B has 3 significant figures. All right, now this last one, the smallest markings are 0.01 centimeters. Right, the distance between the 2 closest space line. So on that measurement, we might need to, let's see, 1, 2, 3, 4. So that looks like it's right on the line, 4.24 centimeters. But we need to go to 1/10 of the smallest marking. So I have to go in and add another digit. And it looks like it's right on the line, so I'm going to make it a 0. And that's what can be difficult sometimes, is when to know that you need that 0 and when not to put too many zeros on. All right, so with the error shown, 4.240 plus or minus, oh, wrong one, plus or minus and our units. So this number from ruler C is required to have 4 significant figures showing, right? So that is the purpose of our lab today, to read devices to the correct accuracy. And that means if you're given a nice ruler with all these markings, that you show that 0 on there if it's appropriate, that you show the correct number of significant figures. I can scroll down. Okay, so the guidelines for significant figures. We're always going to read from the left to the right. And if a measurement is greater than 1, we're just going to read those digits and count them all. If it has a decimal point. So this one has 3 significant figures. In this case, there is a decimal point, and the 0, we don't need that 0 there to show us how big it is. It's only written there because it was measured. So that has 2 significant figures. 2 figures were required in that measurement. This one must have 6. All of those zeros are required in this measurement. If they weren't measured, they wouldn't be written. Does that make sense? Okay, if the measurement is less than 0, then you start with the first non-digit 0. So these just have 2 significant figures. The leading zeros are not significant. And you could think about that like a number such as 500. Right, what if we had 500? Well, that 5 is significant, but all the zeros in front of it, which could go on forever, those are not significant. We don't need them. Now, one reason we need them in these small numbers is to tell us how big that number is. So 0.011 milliliters, that's not a big number. That's a really tiny, that's 11 microliters. It's small. So we need those zeros there to tell us that it's a small number. we'll look more at that when we do scientific notation. All right, if there's no decimal place, then we're just going to count left to right. And if there's a trapped 0, then those zeros would be significant. And if there are trailing zeros and no decimal point, then it's ambiguous. We don't know. We have to communicate that information in another way. Oh, no, I wrote that wrong, didn't I? This should be, let's see, I had 4.2 plus or minus 0.1.
Mm-hmm.
Did I get those all wrong? I wrote them all wrong. Yeah, so it's not 1/10 of this one, it's 1/10 of that one.
Mm-hmm.
So let me rewrite these guys, because it sounds like I was looking at this line. See the line?
Mm-hmm.
Here's the line. That's the line where our object would come to. So that's the measurement we're trying to capture here. And
all right.
I know, I'm so sorry, I made a mistake. But thank you for catching that and asking.
That's okay.
Or
It's okay.
0. Yeah, it's just that last digit that's going to be.
Yeah.
It is significant, but it's uncertain.
Yeah.
Oh, 0.0.
0.01.
1.
Yes.
1 0.
All right, thank you. All right, so let's go ahead and identify, maybe I'll leave the rules up here. How many significant digits are in these numbers? So if you want to use the annotate, you can go ahead and fill these in too. Maybe I'll start with this one. This one has 1, 2, 3, 4 significant digits. Great, so you see B was 3, that captive 0 counts. It was a little hard to read, so I went ahead and typed it in. This has 4, that trailing 0 is significant. This has 5, right? That's measured very carefully. This also is measured very carefully, right? It has 5 significant digits. This one has just 2. So these 2 are significant. The leading zeros just tell us it's small. It's a small number, but we know it's measured to 2 digits. And it's hard to measure small things, right? It's difficult. It's more difficult. So the leading 0 does not count, but the trailing zeros do count because there's a decimal place. All right, so we have some basic units of measurement. This relationship is very important. So mass, we might talk about mass in grams or kilograms. Volume, a liter is, normal size, kind of big. And then a milliliter is pretty small, right? It's 1 cubic centimeter. We have some important relationships, though, with milliliters and centimeters cubed, or in the health sciences, you might hear of cc's, or also engine displacement measurement. So for example, you might have a 500 cc motorcycle. It has 500 milliliters of piston displacement. So that relates to the power. Just some examples, but this is super important. This allows us to go from measurements with a ruler, right, for an object, to measurements of liquid. So those volumes can be interchanged through this equation. And it's useful to write it down and remember it because it's easy to forget, and then it just seems impossible. Now, volume can change very rapidly because here we're looking at 1 centimeter cubed, but if we took that distance and we tripled it, our volume would be 27 times that volume. So volumes can change very rapidly. Here are, so a couple notes on this page. These are all the, these are English equivalents. So we'll see a gallon of milk in the store here in the States. Pints, pint of ice cream, cups in our recipes. But it says no, normally you have to memorize that. I will give these to you. If you need these values, I will provide them. So you don't have to memorize these units. Now maybe you use them and you get to know them, but it's not something I'm asking you to memorize, even though it says to memorize it here. All right, we talked a little bit about temperature in terms of heat. We have a couple different temperature scales. And I'm not going to ask you much about Fahrenheit. In science, we talk about Celsius, but then when we do calculations, we have to calculate in Kelvin. And so I think we'll revisit that idea a little bit. Oh, you know what? I'm going to go to Kelvin. Right, Kelvin equals degrees C plus 273.15. So that's the main one to go between Celsius and Kelvin. That's our freezing point of water. It's large. There's actually a lot of heat available even at freezing. And then this is just going to add 100 so that the boiling point of water is 373.15 Kelvin, even more heat, a lot of heat. And then 77 degrees is quite warm, 25 degrees. That is what we accept as room temperature in the lab, and it's quite warm. Usually our classrooms are closer to 68 or 70 degrees, and so it's quite a bit cooler, but it's still like 21 degrees. Our lab is usually about 21 degrees C. And so this is 25 is our standard, and that is 298.15 Kelvin. Does that help?
Yeah, that's clear. Thank you.
Okay, good. I hesitate to give you the Fahrenheit because I never remember. I have to rederive it every time. So I just skip over that. But if you need the formula, I'll give you the formula. Oh, thank you, Zed. That's right. That's good. And then that gets complicated because significant figures are different when we multiply, divide, or add and subtract. So it gets complicated with that formula in particular. So we're going to set that aside for now and focus on bigger conceptual issues. All right. Let's see. So we will be talking about things that are very big and very small. And the best way to deal with that is to just count the zeros. So we as humans, we are limited as animals in what we can think of. And one of the things that is very intuitive is, we have 10 fingers, we have 10 toes. We're pretty good with numbers from 0 to 20, right? We can picture it. If I said I have 15 apples, you can picture it immediately, right? But if I tell you that the electron is 9.1 times 10 to the minus 31 kilograms, like you don't have a vision for that. We just don't have the conception of what that really means. How big is that? So what we do is we convert it into scientific notation and we count those zeros. Because if we look at those zeros, 31 zeros, yeah, you can picture 31 and you know that that's 31 zeros. So scientific notation takes really small and really big numbers and helps them become something that we can work with in our mental space. So scientific notation is a format. It has to be written a very specific way. And that is that the first number goes in front of the decimal place. You cannot have two numbers in front of the decimal place, just one number in front of the decimal place. And then all the rest of the numbers go after it. And then we take a multiplier with the exponent to make those numbers equal what it was originally. Okay, so there's a lot of different ways that people remember this. I usually try to make two numbers equal. That's the most robust way to remember it. If you remember moving it the decimal place right or left, then it can be confusing. Is it plus or minus? So your double check is always available if you look at which number is big, which number is small, and how do we make them equal. So there should be some of that in the prerequisite review from Alex. So let's go ahead and show these as 3 significant figures. And then we're going to see down here that we have to put them into scientific notation to show that. So I'm going to show you a little bit more about the format, when we need that format, and how to express significant figures. But we will do that tomorrow.